we have implemented a method to get neighbors. Now we can use it. We can iterate through the neighbors and we can compute the g cost, h cost, f cost, and we can set the parent for this neighbor. Let's start. Let's remove this debug log of the neighbors. Okay, we know that we are getting all the neighbors, and now we can iterate through them. So let's write here for each loop. For each. All right, here I will store the variable node, and I will call it a neighbor, simply. How I'm spelling it? Neighbor. Okay, hopefully that's correct. And that neighbor in neighbors. Okay, and if you want to remove this line, you can just get this method call and just replace this and remove this. Okay, that's also option. Okay, and then we'll write the if statement, and we don't want to consider neighbors that are not walkable and they are already in closed list. We don't need to recompute these ones, right? We talked about it. If the neighbor is in the closed list, we are not considering it. If it's not walkable, so there is a rock or something, we also don't want to compute anything for it. So if neighbor is not walkable, so exclamation mark is walkable, or is in a closed list, so if a closed list contains our neighbor, simply skip over this iteration, just simply continue, or just write on the one line like this, continue. And yeah, in the get neighbors, we have already implemented this condition to not add neighbors into the list when they're not walkable when you look at here. So that seems redundant now because we are checking it on the two places. So simply from get neighbors, we can remove it and we don't need to consider it. Okay, so get rid of it here. And we will be checking only here in our find path method if it's not walkable. Now for each neighbor we need to compute the g cost, h cost, and f cost. And for computation of the g cost and h cost, we need to get a distance between the starting node and the candidate node, and from candidate node to end node. And so for getting distance, for computing distance, we will be using Manhattan distance, and that's the formula for it, right? So 14, no, we need to check if the distance x is larger than the distance y. So for the computation of the distance x, we talked about that is absolute value of x1 minus x2, and dst y is absolute values for y1 minus y2. And then you will check if the x is larger than y, and you use one formula, and then other formula if it's not the case. So that's the same thing we'll be using here. So I will create here a new method down here under this curly bracket, and we'll call it simply get distance. So right here, we'll be returning the float, which will be our distance. Call this method get distance. All right, and we'll need to get a distance between two nodes. So right here, node A, let's say, and node B. Okay, and we want to get a distance between them. So first, let's determine the absolute values. All right, so let's write here int dst x equal, and that will be matf dot absolute value. All right, and absolute value node a x minus node b and x. Okay, so that's the x1 minus x2, node ax minus node bx. Okay, and then you will determine absolute value for dst y. Okay, math f absolute value between node a y minus node b and y, like this. Okay, and then you just do the check if dst x is larger than dst y. Okay, the same thing as we done on the paper. Okay, in such a case, you will be returning here 14 multiplied by the dst_y plus 10 multiplied by dst_x minus dst_y. Okay, I'll copy this formula, and in the other case, you'll be returning 14 multiplied by the dst_x and dst_y minus dst_x. Okay, so that's how we'll be getting our distances. Okay, so now we are checking for this. Now the next step here, I want to compute the g's. So first I will compute the tentative g, which is the g of the current node plus the distance between the current node and the neighbor. Okay, so let's write here float and tentative G equal the current node G. So as we are here, right, at the 0, 0 position, I'll just zoom here. Okay, 0, 0 position. That's our current node G cost plus the distance between the current node and the neighbor. So depending on the type of the move. So orthogonal, orthogonal, and here will be diagonal. So these three nodes. Okay, so if we want to get a G cost for, you want to get a tentative G cost, we'll consider the current node and the neighbor. Okay, that's how we can compute the G. Okay, so current node G cost plus get distance that we have implemented now between the current node and the neighbor. All right, and now all the other values. If tentative G is smaller than the neighbor G, or the open list doesn't contain the neighbor, so exclamation mark, and open list doesn't contain the neighbor, then we want to compute all of the values, so H cost, F cost, and want to set the parent. Okay, so if this node we are evaluating is not already in open list, or the tentative G is smaller than the current G, then we want to compute it. So neighbor G cost equal tentative G cost, we have already computed. Then the H cost, so neighbor H cost. So what is the H cost? That's a get distance, so that's the distance between the neighbor, so the candidate node, and the end node. Then the F cost, so neighbor F cost. What's the F cost? F cost is just simply adding together G cost and H cost, so neighbor G cost plus neighbor H cost. Okay, and we'll see the parent, so neighbor dot parent equal current node. Okay, and if open list doesn't contain the neighbor, we'll also add it to the list. So if the open list contains a neighbor, then add it to the open list. Open list dot add neighbor. Maybe you're asking why I'm checking for this twice here. So we want to recompute the G's in two cases, right? When you talked about it, if the tentative G is smaller than the neighbor G cost. That's what we have done here when we have recomputing. We've been checking for this. Where it is? It will be somewhere here. Here. We have been computing the tentative G, TG, and we determine in some cases that it's smaller than the current G. Then we have updated all this G cost, F cost, and parent. So this is one of these cases when you want to recompute it. Okay? And in that case, we already have probably the neighbor in the open list. So that's why we are checking here for open list. If it doesn't contain it, then we want to add it. Okay, but there is also a second case here. You can see we are updating these values when the tentative G is smaller than the neighbor G cost, but also when the open list doesn't contain the neighbor. So that's the first time we are checking this neighbor. We want to update all of this. And then, yeah, this is kind of redundant. In such a case, we could optimize it better. But I want to do it in one if statement, everything. So that's the way to do it. If we want, we can later improve it. But that's the correct way. So you want to update all the costs in this case, or when the neighbor is not in the open list. Okay? But when the neighbor is already in open list, and this is happening, the G's are smaller, then you want to update it still. But you don't want to add it into the open list because it's already in the open list. Okay, part can be kind of confusing, so make sure that you understand what's happening here. Okay, and when looking at this, that we are done. Simply, that's it. So now I can just write here in the last case, when this is coming to this spot here, then I write here debug log. No path found. All right, and these lists we can already remove. We don't need them. Okay, and in a path found now, we can debug log here our closed list, and closed list should be now representing partially your path. That should be also all of the nodes in the closed list. Then you will search the parents from the last node, then you should find the path. as we have been backtracking this, if you remember, we should end up with something like this in the close list, and then you're going from the last spot, and you just get it, you're following the parenting, and you should look up the path like this, and then just not to revert it, and you will get the path. But we will do it in the next lecture. For now, just console log here the close list. Actually, I just revert this, and I can copy this close list from here. Okay, and get a close list here. Okay. So let's save this. Let's get back here. And let's see if we are getting somewhere. Let's play this. And yeah, you are getting the full close list. And it looks kind of correct. When I'm checking this -8 and -9, that should be my worker. Yeah, this is my worker position. And as you can see, the y is increasing by 1. So that should be the path up here. And then we are diverging to here. And then here, just the axis should be changing. So now we have this closest path. We are going to create the now method to follow the parenting from the last node to the first one, get all the parents, and then revert them. And that should get us path. But we'll do this in the next video. So that should be for now.